Well, first of all, a welcome to everybody for taking your time away from your daily lives to join us today and this evening, wherever you are. So thanks for coming for another opportunity to learn a little bit more about what we need to know in the world of gems and gemology, and hopefully expand your knowledge exponentially after tonight and other days that are coming. Today is actually a very unique moment in GemQuest history because we've never had a triumvirate of speakers, let alone three professors, let alone a family, present to us at the same time on a subject. And not only will this be an important day for that change in venue that we've never done before, but they have very generously offered to handle July and August programming. And this will be a mini series on treatments of the corundum family. And today's program is kind of special to them because they've done a lot of research in the area of treatments of blue sapphire. So this is like their forte. And so the thing is, people would ideally like to have a Kashmirian blue, sleepy looking, amazing blue sapphire. And the general public, when they look at or they think of a sapphire, they think blue. Oh, it's like the ocean, like the name. But the trouble is, it's a spectrum of colors that most people aren't aware of if they're not educated in gemology. So our job as providers and sellers and retailers and designers and jewelers and gemologists is to educate that public and let them know more about it. And to help you with that, today we've been very fortunate in getting the Mansour family to the three professors. I call them the three models because they're all like very photogenic. And to present us a very well-rounded scientific as well as informational presentation on treatment of blue sapphires. But again, something varying from the norm. Today we're going to have something we've never done before either because we're nonpartisan. But I think the kind of people that are watching today might be interested in what's going to happen in this next few minutes in a public service announcement. Because Mindat, who every once in a while hosts an amazing trip somewhere for gem collectors and mineral collectors, is once again going to Madagascar, one of the most amazing locations in the world for those exact things. So before we start with the amazing triumvirate of beauty and brains from Istanbul, we're going to ask, I think, Ida Chow, who is organizing this trip, to give us just a couple of teaser minutes as to what's going to happen on this trip. Ida, would you unmute and tell us just quickly about the trip that's going to go to Madagascar, which I'd love to go on, but I'm too old. Ida.
Hello everyone. Actually, I'm Ida from Mindat, and every year we will do quite a lot of different Mindat adventure trips around the world. And with this time that after COVID, we will back to Madagascar again. This is our third time to go back to Madagascar. The date will be start in August 5th to 18th, about 2 weeks. And within these 2 weeks, I will take people go to the southwest part of Madagascar. Other than you can see all the famous national park and all the lovely, beautiful tourist area. I will take everyone go to the Tomaning Mine, Sapphire Alikaka area. And also, this is the only time and also the first time that is allowed people, actually a big group, together to go to visit the Emerald Mine. This is really fascinating things for us to visit this locality. And if anyone interested about this trip, please email me, is accounts@mindat.org. Later on, I will put the information in the chat room. So everyone who interested about to grab all the information about this trip, please email me. And you can see in the chat room coming up, Jolene already put the emails on there. And the date I also will put that on there. And any question you'd like to ask me later on the trip, just email me. Thank you. I just don't want to interrupt you guys to today's program.
Well, I've been to Morocco and Myanmar with this trip. They're amazing. They're well organized, and you get a chance to see where things come from. And I think it's sort of an exciting opportunity for those who have the time and the energy to have an opportunity like this. 'Cause I wish I could go, but I'm not. I'm too. I'm not fit enough to go through the rigors of traveling out in the back of Madagascar. Although I really would love to do it. Anyway, that said, our focus today is on treatments of blue sapphires, and I now want to hand the microphone, if you will, and the video over to the Mansours to please share with us and have fun with us, teaching us about treatments for blue sapphires. Please.
So thank you very much, dear Ray, for the nice introduction. We feel truly privileged to be sharing the little bit that we have learned about sapphires with you today. And we thought very deep about the kind of presentation that this is going to be. And we have created a mix between what we usually do in terms of a comprehensive scientific analysis and the kind of a pop culture that information that is usually more sought after in the trade. So, and since this is going to be recorded and broadcasted later, so we thought we will be presenting some of the information for the first time that is not published anywhere. And these are results of comprehensive calculations that we have done, and we hope you will enjoy the journey as we do. So,
let's just share the screen
yes,
with you.
let's begin. So I'm Mubashir Mansour and my sisters.
I'm Mahia.
And I am Maya.
I'm in the final stages of doing my PhD on material science and engineering here at Istanbul Technical University. And I'm also doing my second major in physics. And we have different specializations.
Yes, absolutely. So my second major is in geological engineering, and my sister Maryam.
Yes, mine is in mining engineering, and I'll be starting my graduate program in radiation science and technology. I hope to work on the radiation on diamonds, which is very exciting for me.
Yes, so we have tried to.
Yeah, but by principle, all three of us are metallurgical and materials scientists or engineers, if you may.
Yeah, so we have tried to conquer gemology from all sides.
Absolutely. So I would like to welcome everyone again, and our today's talk will be about the treated blue sapphires and creating velvet and royal blue sapphires in furnaces.
So let's begin.
So let's start from the very, very basic. All matter is made up of atoms, but what are atoms? Atoms are composed of protons, neutrons, and electrons. Protons are positively charged, neutrons are not charged at all, and electrons are negatively charged. So when we talk about colors, we are actually dealing a whole lot with the electrons in the atom.
So as we can see on this diagram right here, I hope you can see my cursor. The sunlight that we have actually has an energy of about 2 to 3 electron volts. Now, there is this very basic principle in quantum physics, which says if the light coming in has enough energy to push an electron to the next allowed energy level, then the light is going to be absorbed. If it does not have that energy level, that amount of energy, then the light is just going to pass and it is not going to bother being absorbed. And this is actually the basis for a lot of the comprehensive optics that we see in the world of gemstones. This is very much analogous to this jumping gentleman. If the sun energy is enough to push an electron from one of its locations to the next place, then there is going to be this bouncing electron in the process, and that bouncing electron is going to absorb some energy. That energy will be translated into what we call absorption spectra and all those beautiful colors that we are very familiar with. Now, if we have a particular material that has a minimum energy of more than 3 electron volts in terms of the energy required for the electron to bounce from one state to the other, then that means the material would become transparent. If the energy required to push an electron from one state to another is less than 3 electron volts, because that would be equivalent to the energy that sun can provide, then the material would not be transparent. So imagine metals. All of the metals do not require an energy of 3 electron volts to excite, to change the position of an electron. That is the reason why metals are opaque. But if you look at the gemstone, like sapphire, like diamond, they can be transparent. And the reason is the energy required to bounce an electron is so high that the energy of sunlight is not enough to do this. And therefore, these gemstones are inherently transparent. So transparency has a lot to do with the energy required to make an electron bounce. So in simple terms. Well, that means
That means that the sapphires are colorless because they have a band gap energy of about 9 electron volts, while sunlight has an energy of about 2 to 3 electron volts.
so this right here, this is a very important type of a diagram that physicists use very commonly when describing color and other optical phenomena. It's called a band structure. These lines down here, they are the occupied electron states. And these lines up here are the unoccupied electron states. The difference between, and in between, is a forbidden place, a forbidden position. An electron from down here to be bounced to the top side requires 9 electron volts. So since sunlight does not have that kind of energy, the light will just pass through. And that makes sapphires transparent. If there is no other impurity in position, in place, then sapphire would become transparent and fully colorless, sure, isn't it?
So exactly. So basically, in between 0.15 and 4 micrometers, yes, the sapphires have to be transparent.
Yeah, so this is the main. Now, what happens when there are impurities in position? When we have impurities, then this 9 electron volt gap starts to diminish.
Yes.
So once that diminishes, then we have a whole lot of different optical phenomena. We have beautiful colors that we are very fond of in the world of gemstones. Now, why do they happen? Why do these colors form?
So they're basically all fundamentally dependent to the defects within the structure of a material.
Exactly. Now there are very interesting phenomena here. We can have, let's consider those solids, those beautiful atomic arrays. If within these atomic arrays, we have some imperfections, those imperfections that we call defects are actually what give rise to the colors that we observe. Now, imagine a beautiful ruby. A beautiful ruby would have one chromium sitting in place of an aluminum. So that chromium should not be there if it was a perfect crystal. That chromium actually causes a defect. That is a defect, as the physicists call it. So those defects actually tend to create these changes in the band structure that we just mentioned. And those changes in the band structure give rise to color. There are all sorts of different defects in material. They can be substitutional defects, they can be interstitial, which just go and place themselves. Yeah, they can be smaller, they can be vacancies, they can be all sorts of things. And each one of these defects has a different contribution to the UV spectra, has a different contribution to the optical and electronic properties of a material.
All properties of the material.
Yeah.
So basically, to put it simply, we seek, we usually love this term, we always use it. We seek perfect imperfections, because within a structure, if we don't have the defects or the imperfections, then our material would not have the wonderful optical properties that we perhaps desire.
That's also a very beautiful analogy when we consider people. People with their defects are what makes them special.
That's very philosophical.
Yeah, it's the same with gemstones. It's the defects in the gemstones that make them special, that make them beautiful. And today,
we're actually very fortunate to be able to observe these defects in the atomic scale, atom by atom, by using transmission electron microscopy. So in the pictures shown here, where there is light and dark spots, each of them represents each atom and each vacancy.
So,
or
yeah, this is
structure.
amazing.
Mhm.
Science has come to the point where we can actually look at atoms. And these images are actually what we see as these, each individual light spot is an atom by itself. And then look at this, for example, suddenly there is something missing here, a black spot. Well, that's a defect. Well, that defect could be creating all sorts of colors, all sorts of different interesting phenomena in the material. And that's what we will be trying to dive deeper into. But since our today's talk is about blue sapphires, what is the defect that creates the blue color in sapphire? It turns out it has a lot to do with the incorporation of iron and titanium in the alumina structure, in the aluminum oxide structure, in the sapphire. I mean. So over here, if we look at these balls, the grayish ones are aluminum, the red ones are oxygen. This brownish one is actually a titanium, and this teal color one is an iron. If we have an iron and a titanium sitting side by side in places of the aluminum atoms, then we would have these beautiful changes in the band structure. So remember, last time when we saw this band structure, in between there were no lines. It was completely empty. And we said the incoming light would require 9 electron volts. And since the sunlight does not have that kind of energy, there would be no optical transitions. Electron would not be able to jump. And that means the gemstone would be transparent and colorless. But since we included now titanium and iron, this structure changed. And now we have these lines in between, which are the allowed states. It's like the electron now has these very, very nearby ladders onto which it can climb. And it can climb with very low energy, with energies of about 2 to 3 electron volts, which is equivalent to the sunlight. And that is the reason why we can actually create the blue color from the iron and titanium that come together in the sapphire structure. Okay, so the iron being in 2+ and titanium in 4+ charge states create this beautiful hump of about 570 nanometers in the UV spectra that creates the blue color. Because consider this, over here on the 700, 600 nanometer side, especially this side, we have the red colors that are being absorbed. Over here, we have the greenish ones that are being absorbed. And all that is left, this transmission window, is in the blue range. So we have the blue color that arises from the iron and titanium incorporation in the sapphire structure. Okay, there was this beautiful theoretical study that was published by Professor Patalong in Thailand, and they had even calculated very beautifully how the energies are in this respect. And it turns out that they can reproduce the UV spectra of a blue sapphire just by considering this iron and titanium sitting side by side. So it's very good foolproof information that iron titanium intervalence charge transfer is the cause for blue sapphire. But believe it or not, this is not the only thing.
Exactly, it's not the only thing.
Yeah, there was this other study published actually quite recently, which still does not challenge the presence of iron and titanium, but it challenges the charge states. And this study, it was a beautiful study, very detailed experimental study. They actually show that it could be iron 3+ and titanium 4+ that creates the kind of energies necessary for that hump that we observe. So, it could be that both are actually playing a role here, both iron 3+, titanium 4+, and also iron 2+ and titanium 4+. And this hump could be a contribution of all those different charges in the iron and titanium solid solution. We'll come to there as well.
So before diving deeper, we should understand why milk is not transparent.
Yeah, exactly. So it's basically due to the scattering of light within the milk liquid.
Yeah. So why is it being scattered in milk?
Because milk, we're talking about proteins, the fat molecules, the lipids. The interaction of light with the liquid due to the secondary particles causes a lot of scattering. As a result, we have this very milky milk.
Yeah, and this is important to analyze because a lot of sapphires that come from Sri Lanka or from Madagascar have a very similar kind of a milky appearance to them.
So basically, the reason why they use the term milky sapphires is actually this due to the same analogy, due to the same sapphire.
So sapphire in itself should be very transparent, but we just mentioned there could be secondary particles inside. And those secondary particles tend to create this milky appearance that is very common. So for example, since Mindat is going to Madagascar, we thought let's put one of our sapphires that we got from Madagascar right here too. Now, this beautiful giant chunk was actually mined from the northern Madagascar. It was from very close to the Ambatondrazaka region, but that milky appearance was quite fascinating. And these sapphires are very common in the mining zones in terms of both the quantity and the material that is being mined. A lot of these sapphires mined both in Madagascar, in Sri Lanka, and also in other places in East Africa, even in Nigeria, actually every single place,
every deposit.
Yeah, has a lot of these milky sapphires. And these milky sapphires, there was this beautiful paper by Dr. Palki. They have analyzed what those secondary particles inside these sapphires are.
So they have found that the majority of these secondary particles are actually titania, which is rutile. So it was very interesting because it's highly found in many, many different mines.
Yeah, so sometimes in some mines, we have a combination of hematite or maybe hematite and rutile or ilmenite. So it could be a variety of the titanium containing inclusion inside these sapphires that creates these milky appearances and diminishes the clarity very significantly. So we have to get rid of them. And a great deal of the sapphire treatments are all about how to get rid of that rutile completely so that we can get the perfect clarity, right?
Absolutely.
Yeah. So here, for example, we love these rutiles when they're in their needle shape, like these beautiful images by the Lotus Gemology by the Hughes family. And these ones we love, but most of the time they create a sleepy color if they create a very sleepy gemstone if they're too much in quantity. And even worse, if they're very scattered, very small in size, then you have these opalescent sapphires that have recently become quite trendy for some reason that I do not understand.
It's actually very pretty when you think about it.
I don't find them pretty, but anyway, those are perfect for heat treatments actually, because these opalescent sapphires tend to have very small crystals of rutile in them. And since they're very small crystals, you can actually dissolve them in the sapphire much more easily. But we will come to that very soon. So the major part of these sapphire treatments.
It's also the Guza treatment, which is very, very popular and very famous in the sapphire industry.
And this is what the majority of people call the standard heat treatment of blue sapphire.
It's become the universal.
Yeah, it has become the universal treatment. And there are these beautiful images.
Before and after.
Yeah,
images.
actually, I highly recommend, I especially put these pictures because I wanted to emphasize this paper by Vincent Pardio, who did a very beautiful study with the father of heat treatment in Thailand, someone who actually passed away in 2021. But if you actually read this paper, you will find a lot of the details that we will not cover today. So in principle, what we just wanted to mention, now look at the colors. First of all, for example, this cushion type shape, you can see that how darkened it has become after the heat treatment. These changes in the color are primarily because of the dissolution of the rutile that was there in the crystal. Why is the dissolution important? We just mentioned the blue color is caused by iron and titanium that are in the structure in place of aluminum in the sapphire crystal. If we dissolve all of those titanium atoms that are positioned in the rutile and we just let them free in the sapphire, then that means they would be now contributing to the formation of a blue color. And that is a beautiful blue.
Absolutely. And it's not only the color that is enhanced, but the clarity as well, because the microcrystals are being dissoluted and therefore the clarity increased as well.
Exactly. So how do people do these treatments?
So basically, the Luck mini furnaces in Sri Lanka are quite famous, which are actually oxypropane furnaces.
Exactly, or perhaps the molybdenum disilicide furnaces or the electric furnace.
So for example, in these oxypropane furnaces, people do all sorts of heat treatments in Sri Lanka. To this day, the majority of heat treatments of sapphire are taking place in these rather old looking, a little bit dangerous looking, which are actually dangerous furnaces. Unfortunately, I've heard far too many accidents arising from these oxypropane furnaces because people don't control the gas inlets, and you're dealing with a very explosive mixture. You have propane coming in from one side, you have oxygen coming in from the other side. If you don't have the necessary backflow stops and all sorts of those things, then it becomes quite an explosive mixture. But the more, if there is anyone interested in doing these experiments by themselves, I do not recommend going for an oxypropane furnace at all. Just go for a beautiful electric furnace. It does the job much more elegantly as well. Now, this on the top is the system that we are using, that we have developed. And we try to do these in all sorts of different environments. We do all sorts of different atmospheric conditions and so on. But we'll go deeper into that in a bit. But I highly recommend the book by Ted Temelis on this issue very much because
It covers a lot of different furnaces.
yes, and he also covers the processes in very good detail for anyone who's interested to do these by themselves. I think the information over there is comprehensive enough to actually do these treatments by yourself. Now,
So before talking about the heat treatments of blue sapphire further, we should understand the heat treatments applied on chocolate.
So this is actually a very yummy heat treatment, perhaps.
yeah, so why are heat treatments of chocolate so interesting? Because we wanted to show what a phase diagram is. Now, a phase diagram is a very important part of materials engineering.
A very important tool, actually, to
Exactly.
understand the process.
And in the heat treatment processes, what we are basically doing is actually trying to engineer different materials through doing some sorts of heat treatments or whatnot. But let's look at this diagram together. On the y-axis, here we have the temperature. And on the x-axis, we have the percentage chocolate that is being mixed in vanilla. It's showing us that if, for example, I have 5% chocolate, 95%, so that means I'm on this line, and 95% vanilla, if I stay at about, let's say, this temperature here, which could be 30 degrees, then I will not be able to dissolve all of my chocolate into the vanilla. But if I go up to, let's say, 50-something degrees, then I would be able to dissolve all of the chocolate in the vanilla. And I would have just one material. That would be the vanilla that is composed of chocolate in the solid solution. If I go even further higher in temperature, then I would just get hot chocolate. So that's a beautiful way of describing the types of chocolate we can make from the combinations of vanilla. So what is a phase diagram again? It's just showing us what happens if we mix two materials. It's a map. It's a map that we can follow. And these maps are so common in the world of materials engineering that without them, we are blind. And we do all in our power to make more and more and more maps for different conditions, for different situations, for different materials. One example are, for example, the different steels, the stainless steels that we are very fond of. All of them have similar maps. These foundries use those maps. Gold, rose gold, when someone is trying to make a rose gold, they follow a similar map. So everything from chocolate to stainless steel to sapphire treatments, we should follow the phase diagram maps. Now, coming back to these sapphires here, we are mentioning that we are dissolving rutile, the titanium dioxide, into the alumina structure, into the sapphire. How can we describe that in a phase diagram?
Well, the problem is that there is no solubility in this phase diagram for rutile.
Actually, this is very interesting because what is this diagram showing me? It's saying that, for example, look at this particular side. It's 100% alumina. This means this side we have 100% sapphire. And as I move to the left, I increase the concentration of rutile. But the problem is, anywhere I am on this map, I sit somewhere in here. That means I do not have just alumina or sapphire. I have both this aluminum titanate kind of a compound along with sapphire. So that means I have two materials.
Yeah.
Now, I want one material. I want it all to be sapphire. I want it all to get into the solid solution. But the problem is, any phase diagram that you open for the combination of titanium dioxide and aluminum oxide, that is sapphire, we always see these binary compounds, these two types of different material. So we do not see these becoming a solid solution. So this is a problem. And a great deal of gemological literature has used this diagram to explain the heat treatments in blue sapphire, which is not correct. Because, as we will show in very shortly, in order to explain the heat treatments of blue sapphire, one should remember something, and that is, you have probably heard of it, it's so common knowledge. Heat treatments of blue sapphire take place in reducing environments. What does that mean? Reducing environments mean we have very little oxygen in the furnace when we are doing heat treatments of blue sapphire. So that is known from an experimental perspective. People who are doing these treatments know it very well, that they have to reduce the oxygen in the furnace in order to be able to create these beautiful blue colors. But when we are trying to explain what's happening, we rely on these phase diagrams that are usually plotted for 1 atmosphere oxygen. And that is the problem. So let's go on and see what happens if we recalculate these diagrams in the absence of oxygen.
So basically, if we understand the mechanism of dissolving sugar in water, we are actually able to explain the process of dissolving rutile in sapphire. It's a very, very simple way of looking at it, but perhaps the more simpler we look at it, the better we'll understand how it works.
To be honest, there is absolutely no difference between the Geuda treatment and dissolving sugar in water. It's exactly the same. Exactly the same. Let me give you an example why we say so. Let's say you have a cup of water and you put in a lot of sugar in it. Up until a particular amount of sugar, you can dissolve it, right? So you can just stir it and dissolve whatever is in there. Sure, good. But if you keep on adding more sugar, it becomes impossible to dissolve even more of that sugar in water, right? So what would be the solution? How can we dissolve even more sugar in water? One perfect way would be
increase the temperature.
Yes. So we would increase the temperature. That's exactly what we do with sapphires. They have too much rutile in them that nature cannot spontaneously dissolve it more than it is.
Energy.
It needs energy that is not available around the formation of sapphire. So instead, what we can do is let's heat it up so that more of that material can be dissolved in sapphire. So in this context, by sapphire, we mean water, and by rutile, we mean sugar. So it's the same thing. Now, we can go one step ahead and say the following. If we have reached the maximum saturation of sugar in water, what else can we do apart from increasing the temperature? We can change the pH of water. By pH, I mean the acidity. We could drop in a little bit of lime. So we could just do a little bit of kitchen trickery to even dissolve more of that material, of the sugar. And it's the same thing with sapphire. So let's look at the diagram on the left. If we actually look at the solubility, so over here, this hump that we see here, This hump actually shows how much solubility we can have of the rutile in sapphire. And it turns out that the maximum solubility actually happens when you're heating it in air, actually happens at about 1850 Celsius, which is a very high temperature. Why is this a very high temperature? The best furnaces cannot usually exceed 1700 Celsius commercially. So that's the problem. And also another problem is the maximum concentration of rutile that can be dissolved in air is actually very limited. It's quite a small amount, but
Dissolving rutile in sapphire is actually oxygen partial, that it's dependent on the oxygen partial pressure, and therefore it changes by even more than 250 times. Therefore, it's a very, very efficient process.
So these are the diagrams that I mentioned that has not been published yet, and you're the first to actually look at them. We did all sorts of different thermodynamic calculations, and we realized that if you reduce the oxygen inside the furnace, what's happening is a very fundamental change in the material, in the sapphire. And that fundamental change increases the amount of rutile that you can dissolve. It increases it by 250 times. And what's even more, it reduces the temperature of maximum solubility to about 1630 degrees Celsius.
Which is highly desirable because most furnaces can go up to these temperatures.
Very easily.
The process becomes much more easier in terms of practicality.
And we were talking with Ted Temelis about these observations of, the calculations that we have had. And he mentioned something quite phenomenal. He said, well, you mentioned 1630, and I call that in my book the magic temperature. Because I have witnessed this from an experimental side, that if you reduce the oxygen and you go to 1630, you get the best results. Well, no doubt. We get these out of the calculations as well. So this is a beautiful harmony between experiment and calculations on how the solubility of rutile depends and changes based on the oxygen fugacity in the furnace. So for the people who do sapphire treatments as a hobby or professionally, I highly recommend to do not ignore the impact of oxygen and the oxygen concentration. That is one of the most important parameters in the sapphire treatment world that one can possibly imagine. And there is a lot more to it that we will talk about next month when we're talking about the fancy colored sapphires. But the oxygen parameter is a lot more important than temperature, believe it or not. Now, if we extend the same diagrams even more, we can actually plot these new diagrams, which are beautiful maps of how we can create complete solubility based on the concentration of rutile we have in sapphire. So what it's basically showing is that you need to have a low oxygen partial pressure. This x-axis here, the -30 means almost no oxygen. 0 means a lot of oxygen. And it means if you have a lot of oxygen in your furnace, to get to this full solubility, to this shaded, to this wide region, you should have a temperature over 1600 Celsius. But as you increase the titania concentration to, let's say, 500 parts per million, then you can never reach full solubility. So that's the reason why, if I heard this many times, and we have also experienced this ourselves from sapphire enthusiasts, that, for example, they take a sapphire, they do the heat treatment in air, and they say, I cannot get rid of that rutile. Well, no doubt, if you have too much rutile in there, you need to play with the oxygen in your furnace. Otherwise, it's impossible to dissolve it all. But the moment you reduce your oxygen concentration by even a little bit, you get full solubility. So it's an essential part of the process. Now, we can go further, right?
There was a paper published by Professor Emmett where he had actually put forth these beautiful photographs of rutile including inclusions before heat treatment and after dissolution, where they have turned blue in color.
Yeah, so something that Dr. Emmett realized was that if you reduce the oxygen more than a particular concentration, so we just mentioned reducing the oxygen is good, but how much? He realized that, okay, if you keep on reducing the oxygen more and more and more, you suddenly,
bad effect.
yeah, Exactly. It suddenly became opaque. Your sapphire suddenly became opaque. And that is an undesirable phenomenon. And the reason for that is something that we will come to very quickly. But something that I just want to mention. Let's return back to the water that we mentioned. We have water, a glass of water that has sugar dissolved in it. What happens if we leave that saturated? So we heated up the water,
Dissolved so much
yeah.
sugar,
So
it
now we
became
have
an oversaturated solution
And now we just leave it on the tabletop overnight
to cool.
to cool. The next day that we come, what do we see? We see these tiny sugar particles in the crystals in the water glass that we had. That means the excess that we had dissolved at higher temperature suddenly precipitated out of the water, out of the liquid. The same can be done. The same kind of observations we have also for sapphire. So if you, for example, dissolve all of the rutile, but you reduce your temperature very slowly, then what happens is all of that excess rutile that you dissolve suddenly reprecipitates, reappears in your sapphire. So that also makes it very important to cool down your sapphires from high temperature very quickly. Otherwise, if you don't quench them, as we call it, by quench, it means cooling it down very quickly.
Very rapidly.
You would get these reappearing. But sometimes you want them to reappear. When do you want them to reappear? When you want to create velvet blues. What are velvet blues? Those sleepy sapphires are actually containing these very small particles of rutile that have been recrystallized in a very controlled manner. Nature does it beautifully in some geologic locations like the Kashmirs, but you can also do it in your furnace. And this paper by Professor Lagerlof back in 2010 actually plots the diagrams for how to do this, the kind of timings that you should do in order to have precipitates of rutile as you desire. You can use the same methodology to create star sapphires. So you have too much rutile, you go to a high temperature, you dissolve it all, and then you start cooling very slowly, and then you create these rutile crystals that contribute towards asterism. So it's all about how you treat and how you cool.
It's basically all about designing the appropriate parameters for the experimentation process.
Exactly. Now, we mentioned about iron. We didn't mention about iron, but we mentioned how if reducing the oxygen is actually not always good. Reducing it below a certain limit actually has a very negative consequence, and the sapphire becomes opaque. But why does it become opaque? So again, for the first time, let's look at these diagrams. These are for iron in the sapphire. If we have too much iron, we should stay on this part which says corundum. If we go to the left and we go into these boundaries which says iron plus corundum, or anywhere on the left of this line, then we would have these tiny crystals of iron appearing in our crystal, or tiny crystals of hercyanite, an iron spinel, appearing in our crystal, which is extremely detrimental to the appearance of those sapphires. So that means we should go down in the oxygen concentration, but not so much that we actually create precipitation of the iron in the crystal. Titanium requires low oxygen to dissolve, but iron is the opposite way. It requires too much oxygen to dissolve. So we should find the balance between the two. And that's the secret behind most of the successful heat treaters of blue sapphire. They know those perfect places to be. And these perfect places change based on your mind, because the concentration of iron and titanium changes as well. So you have to be careful with that. Now, this is, for example, one example where we optimized by calculation. If you have, for example, a hypothetical case, 3,000 parts per million of iron, 2,000 parts per million of titanium, which conditions would create your solid solution? And if you have too little oxygen, if you're somewhere here, then we would expect precipitation of iron, and under transmission electron microscopes,
we can actually see the iron.
Exactly. And we thought, well, let's do it ourselves. And
this is the result of our own experiment.
Yeah.
In which we actually created gray sapphires.
This gray sapphire was very fun. I also shared it on social media, which created a little bit of a tension in some of the viewers. But it's actually interesting because you can create these nanocrystals of iron inside your sapphire. So it's a synthetic vernal sapphire where we intentionally crystallized some iron nanoparticles, and that created those gray shades. And if you see a gray sapphire, which looks very similar like a spinel, it could very well be treated at a very low temperature. So be warned about that. Okay, let's now go towards a different process, the Punsiri process.
Can I just take a second there, if you don't mind?
Yeah, sure.
Before you leave that process, if someone is gemologically assessing a stone, what are the telltales that they've had that treatment that they need to look for?
You mean the gray one?
Oh, the blue ones that were treated with the previous process.
So the previous process that actually requires very high temperatures to be easily done in a short time frame. So that means you would always have these stress halos and very similar phenomena that are observed in sapphires that have been treated at a high temperature. So stress halos are a very good indication, but also due to the limited amount of oxygen that is present in the furnace, you should always have some concentration of oxygen vacancies. And our calculations show that oxygen vacancies are responsible for a chalky appearance under UV vis. I mean, under fluorescent lights. That also shows that if, for example, you shine a UV light and you see some chalky appearance, and you also have these stress halos and indications of high temperature heating, then it is extremely probable that the material has gone through this sort of a heat treatment. Something else that I just want to emphasize, we did mention about this, but it's very important to note something. Look at this diagram here. It's telling us that even if you're at 900 Celsius, and you go down to about, let's say, 10 raised to the power of minus 17 atmospheres of oxygen, that means very little oxygen, you can, in principle, get complete dissolution of sapphire, of the rutile in sapphire. Now, that is alarming. Why? It means that if someone waited for, so if you reduce the temperature, the speed goes up. The speed goes down a lot. The kinetics change. So if you reduce the temperature, you should wait a lot for the same process to happen. If you increase the temperature, the same thing usually happens in 6 hours at 1700 Celsius. If you go down to, let's say, 900, you should probably wait for a year.
So before we proceed, looking at these phase diagrams, we're actually considering this from a dynamic possibilities that could occur. However, we don't know the time frame. Because of the time frame, we have to take a look at the kinetics of the process, as Basha just mentioned.
And the kinetics are very interesting because it means if someone waits long enough, they can do complete dissolving of rutile even at 900 Celsius. And 900 Celsius will not leave a great deal of telltale signs. So, we are not very much into the gemological identification world, but we share our knowledge with the gemologists as much as we can, as much as we know, of course. And that leaves some alarm bells most of the time because sure, if the material has been heat treated at a high temperature, you would know it for sure. But if it was treated at a very low temperature, in theory, it could still happen. There is nothing against it. Some people think that if you reduce the temperature to 1000 Celsius, you can never dissolve rutile in sapphire. That is not correct. You can dissolve rutile completely even at 900 Celsius. And we will show you an example by the end of this talk, which was mind-blowing for us.
Sorry to have interrupted you, but we have an audience that is oriented towards identification and valuation. So it's good to know the processes and understand why. But I think also it's important for them to understand how they can test for it and understand what's happened to the stone so they can appropriately evaluate.
Exactly. So I think, my personal opinion regarding the heat treatments of blue sapphire is a little bit of a pessimistic view because most of the time we are not able to, when we are not able to distinguish between the treated and untreated, the report says no evidence of heat treatment. So we do not see the evidence. But it could have been heat treated. So we have had many situations of this sort where you do the treatments at a very low temperature and you get a no evidence of heat treatment kind of a report. But from a commercial standpoint, I doubt someone would go on to do these treatments at a very low temperature and keep on waiting and waiting and waiting just to get an untreated or a no evidence of heat treatment kind of a report.
It's not exactly very
Practical, yeah. So I wouldn't be worried about it, but it's possible. So I'm just saying.
Thanks. Thank you.
Yeah, my
Thank
pleasure.
you.
Please feel free to interrupt as we move on.
It
It's
would be more fun to have a
conversation
discussion
about things as we proceed. Okay, so coming back, by the way, for example, this case that we mentioned here, we had the nanocrystals of iron reprecipitating in the crystal. This treatment happens at such a low temperature that it is impossible for any kind of a gemological lab to identify the process by virtue of simple equipment that is used today. It is possible in principle through some other sophisticated methods, but I do not know of a gemological lab who does that.
Yeah.
Okay, so let's move on to the Fonseri process. Now, this is a very fun kind of a treatment because it creates these colorless rims on sapphires of dark nature. There are these beautiful photos are actually from Richard Hughes and Sudarat, who had published them in the past. But what is interesting here is we even talked about this with Dr. Emmett, and his idea is that when they're doing these treatments of blue sapphire, while they're cooling, they try to increase the oxygen concentration in the furnace so that they create a colorless rim. That is one possibility, but to be honest, we do not really know what is the cause of these colorless rims. And it could be oxygen changes during heat treatment or during cooling, but it could also be other things that is still open for debate. So this is a very interesting phenomena that I personally do not understand yet. So hopefully we will learn more about it and we'll share it with you as we learn more about it. But if I see these colorless rims, I would be very concerned. Now, recently in 2009, there was the emergence of treatments by pressure.
Exactly.
So people called them the HT plus P treatment or the HPHT treatment. They appeared in Korea, and they have two very interesting characteristics. One, they're very fast, and two, they can create darker colors that are usually not possible by the conventional method. By much faster, I mean the treatment that takes about 6 hours in a Lakmini furnace would only take 30 minutes under this pressure that is being applied in these Korean methods. And they are being certified as, their gemological reports are sometimes just calling them basically treatments, sometimes they're calling them HT plus P. But they're not that difficult to identify, as I have understood. However, what's happening here is something that I just wanted to mention. In this case, sapphire is being pressured while being treated. This diagram over here actually shows how a dislocation looks like from an atomic perspective. Dislocations from an atomic perspective are like highways. They create these atomic imperfections that can go all the way from one side of the gem to the other. And they create highways for atoms to move around. And that means if some process was taking long, now because of these highways, it only takes a matter of minutes to be completed. So the incorporation of pressure actually creates these additional defects that tend to enhance the speed of the treatment process by a lot. And that also means you can dissolve even more of your rutile easily because the process has become very fast. And that means you will be able to get darker colors. So in principle, it's actually very easy to explain why this process is more effective. And the GIT had these interesting observations. For example, the way they do it, they create these crucibles, fill them with a graphite powder. They put them in a uniaxial press. It's a hot press in practice. It's not a furnace per se. And then they create these before-after kind of conditions. The characteristic telltale signs for them are the ghost fissures, but that is a little bit different. We will talk about that in the third session that we will be talking about during clarity enhancement. So it's not that difficult to identify it, but nevertheless, the process is new and it is being studied by our team as well. So what happens is that there is another very interesting paper by Professor Lagerlof, who actually shows that it's a very old study. This is a very well-known phenomenon, even in the 80s, that if you apply pressure while you're doing the heat treatment, the sapphire becomes soft and gooey. And that means you can increase your dislocation concentrations and you can deform it even to a very good extent.
So again, it's all about the defects that are enabling these changes in the material.
Exactly. So what we did, we thought, well, this is such an interesting phenomenon that we would like to do more experiments on it. And a few months ago, we came together with Ted Temelis here in Istanbul, and we did some of these experiments under pressure, the heat treatment experiments under pressure, using this device that you see in the center. This is actually a spark plasma sintering machine, which this shaft over here can create a very high pressure in the center. So we applied the kind of pressure which is being applied in Korea, the 100 megapascals, and we placed the sapphires in rather similar conditions that they do. And look at what we saw. This is actually a synthetic. We did it on some synthetic sapphires, and we are still researching on it, so it will be published soon. But what you see here, these straight lines, we could see shear in sapphire. Sapphires sheared so well. By shear, I mean they changed the atoms just displaced so elegantly that we could see them with our naked eye. And that means the process, any process at an atomic scale should be increased or accelerated exponentially if sapphire goes through this sort of a process. And I hope people don't confuse these straight lines with some natural inclusions, but we'll publish this soon. It was a consequence of the pressure that was applied. So that's also an interesting observation that we are showing it for the first time here. Now, there are, of course, other methods of doing the heat treatments of blue sapphires.
Because the notorious
Yeah.
beryllium
Exactly.
diffusion of ruby and sapphire.
So I just want to recommend this beautiful article by Dr. Emmett and others who actually published this early on, fortunately, during the beryllium treatment fiasco. But what they actually show is that you can reduce the color of the dark blue sapphires through beryllium diffusion as well. And this process, the reason that this process actually works will be a topic of our next month's talk when we're talking about the fancy colored sapphires and what beryllium does to sapphires in general. However, it's enough to note that if you have a sapphire that is very dark, and if you expose it to beryllium diffusion, you can actually get very nice light colored sapphires out of it. So beryllium tends to destroy the blue color in sapphires. And beryllium is not the only element that can do this. A lot of things can. And beryllium is just one of them. So that's also an interesting topic that we'll talk about later on. And then there are, of course, the surface diffusions, the most notorious of them all, I would say, where you can get a thin film of titanium diffused into the sapphire when the sapphire by itself does not have enough rutile or enough coloring agents where you can just put them in by diffusion. These treatments take very long, so they usually require 1 month of heat treatment at about 1700 Celsius. It's not easy, but people go to extremes to do these treatments, and they usually do it on already shaped gems, and then they just do the final polishing once the treatment is done. So these are also very simple to identify. You have facet junction colorers, and they're so famous that I think they do not require much explanation. But something requires a lot more details, and that is the low temperature heat treatments, right?
Absolutely.
So the low temperature heat treatments are a rather new phenomena in the world of ruby and sapphire. people, sure, they know how to deal. The gemological labs know very well how to deal with high temperature heat treatments, but the low temperature heat treatments are new.
Harder to identify actually.
Because they don't leave behind telltale
Research.
signs from the inclusion side. And there was this beautiful paper by the Chiang Mai University where they actually showed how the changes in color of a sapphire occurs as you increase your treatment temperature. So even a very dark blue, if you treat it at a rather low temperature, you can get a complete destruction of that blue sometimes. But even for the worst cases where the transformation of the color is not so simple, you always get some lightening of the color. So this has become a very standard procedure in a lot of the sapphires from Australia, from the many basaltic regions, where you have these inky blue colors. You do the treatment at a low temperature, and then for an extended time, and then you get a much lighter color as a result of it. What happens is, now, since these treatments occur at very low temperatures, about 1200 Celsius or so, and the geological conditions under which these treatments, these sapphires genesis occurs, are also at a very low temperature, it becomes very difficult to identify these sapphires as well. And therefore, there are a lot of researches going on how to identify low temperature heat treatments. People are focusing a lot on zircon inclusions, which is a very good news. Zircon inclusions, doing Raman spectroscopy on zircon inclusions in these sapphires could be a very good way of doing it. Professor Fritsch had published an article that actually showed this is a possibility in the past. It was actually published quite recently. Now, from our own treatments,
Yes, we could see amazing transformations at 900 degrees Celsius, and that is phenomenal.
now, look at the transformation. That, since it has been a backlit image, it actually shows a lighter color, but this blue is actually quite a dark blue. At 900 Celsius, we could not only get a complete transformation to, we not only remove the blue color entirely, but we were able to induce a whole different color as well. And this whole thing happened at 900 Celsius. You send this to a gemological lab, I bet there is very, very small likelihood that they will be issuing a heated report for this. However, the kind of heat treatment that has happened here is more drastic than a beryllium treatment in terms of the outcome. So the low temperature heat treatments are not so innocent, but require a great deal of research because there aren't any good ways of identifying.
Exactly, and perhaps some major advancement in the methods of characterization
Exactly.
are necessary. Yeah.
And we are going to talk about this very shortly, what we think is the absolute perfect way of doing this. But if we look at the quantum chemical calculations that have been done by Professor Yildiz and by Professor Yildiz's group at MIT, it was published in 2019 on a whole different subject, but it is so relevant to gemology that I just couldn't resist putting it here. They have shown what kind of defects from the iron and titanium occur as you heat them in different oxygen partial pressures at a constant temperature of 830 degrees Celsius. For example, they show that iron 3+ is the most dominant kind of iron valency that we would observe, regardless of the oxygen concentration. Now, if you reduce your oxygen partial pressure in the furnace, you would get more of these iron 2+. Same here. If you actually are playing with oxygen partial pressure, you can change the valency of titanium based on oxygen partial pressure and temperature, of course. But these diagrams are very interesting, but unfortunately, the professor's group at MIT only did this for one simple condition, and this isn't enough for us to understand.
For heat treatment process.
But this is so crucial. If we could understand how these valencies change and how they interact with one another in much more complex situations, then we could go a whole different quantum leap ahead of where we are today in the world of gemology. So
So what if we had more of these diagrams for even more complex situations where we can calculate and see how the defects interchange, transform into others?
Exactly. And that is where defect thermodynamics comes in. This is a topic that we are working on very passionately now.
Or perhaps in other words, defect engineering.
Exactly.
Some we love to use.
Yes. So if, for example, consider iron. If iron is in sapphire, it can form so many different defects.
So there are so many different possibilities. For example, take into consideration if there are two iron atoms inside the alumina crystal,
Adjacent side.
yes,
Yeah.
or even one iron and so the band structures that they form are completely different from one another. Therefore, their optical properties are absolutely different.
That means if, for example, we could somehow understand the conditions, the experimental conditions which give rise to a particular defect based on the experimental conditions, based on the heat treatment conditions, then we would be able to know the kind of Raman peaks, the kind of FTIR peaks, and so on, that each defect would produce. And each of these defects that we show here, as they produce a different color, they also produce different characteristic Ramans. They did produce different characteristic FTIRs. They produce different characteristic PLs, and so on.
They are actually unique in all different ways.
Exactly. So what if we could know which defects occur during low temperature heat treatments, which treatments induce or trigger a particular kind of a defect, and then that would be the holy grail.
So actually, it would be wonderful if we could have this database in which we have the exact details, the characteristic expectations that we have for a specific defect, and then we could characterize the material so easily.
This idea that we're putting forward is not new. Even in the 50s, so Kruger and Vink, so Professor Kruger is a very well-known defect physicist who has been cited many times in the gemological literature as well. He had this beautiful book, The Chemistry of Imperfect Crystals. Imperfect because we're dealing with defects, right? So everything that we try to create these perfect imperfections through these processes. But what they showed was that it is possible to do these calculations, but the problem is, from an experimental side that they were dealing with in the 50s, this was extremely difficult. However, today, we live in a different era. And ever since 2006, we have started to see it is now possible. The physics is mature enough to make these calculations possible. And we thought if we can do similar calculations too.
Exactly. We considered if we could perhaps predict the 70 years of experimental data that is on diamonds, and we could actually calculate them on the nitrogen-related defects.
We started this with diamond because diamond has a great deal of published literature. But if we can do this in diamond, it means we can also do it in sapphire. We can also do this in all sorts of other material. Exactly. So we are fortunate enough to have this UHEM supercomputer at ITU, where we actually applied these calculations. And I just have to mention something very quickly, and that is, when we are talking about defects, I just want to translate this equation right here into simple English on the right. That is the following. Any defect that forms in a material depends on these four parameters very, very closely. A defect's formation depends on the temperature and also on pressure. It also depends on all the gases and solids that are around the crystal. So you hear, for example, people talking about these recipes. They say you put your sapphires or your tanzanites or this and that inside a crucible and fill that crucible with blah, blah powder. That is very important stuff because that influences the kind of defects that form in the material. It's very critical information. It also depends on all the defects that are already in the crystal. So that the geological history has an impact to play as well. And then there are also the lattice strains. If the material has been under pressure, not any kind of defects that induce strain, and so on. So studying this from an experimental perspective is so difficult that for nitrogen doped diamonds alone, it has taken 70 years of research. So imagine if we want to do something similar with sapphires, it would take generations. Imagine if we want to do it with other gemstones, it would take centuries. So this is not the way to do it, but instead we can do these calculations from the quantum mechanical perspective. And we tried this on diamond at the onset of the pandemic, and we realized that we can calculate the kind of defects that a particular heat treatment situation can induce in a matter of weeks. And this is what we are trying to do on Sapphire. So I'm not going to do in detail about what this was done, but if there are questions, I'll be more than happy to. We just wanted to show you that, for example, experimentally, it is known that the B center or the N4V is the most stable defect that occurs in diamond that just popped out of our calculations, which had no experimental input whatsoever. For example, we were able to see that many of these nitrogen-related defects, they go up in concentration as a function of temperature, and then they come down. Experimentally, this was known as well, but it was never explained why this happens. We were able to see that this is a consequence of the nitrogen activity in diamond and so on. So the idea is, if we do similar stuff with sapphire, then we would be able to understand a lot more about what is happening during the heat treatments. And then we can go back from there and create the identification procedure necessary, because we would know the kind of defects that would coexist during heat treatment conditions.
So I have a quick question for you then, based on what you've just sort of extrapolated. Is it possible in your near future, do you think, to create a table of Raman signatures of different treatments so that people who have access to Raman technology will be able to do a quick analysis of the treatments that we now know are out there?
It would be possible, not just by Raman alone, but by a mixture of different observations. So the Raman, the FTIR, the UV-Vis, and also a combination. But you know, something else that is important here is the trace chemistry of the sapphire itself. So the trace chemistry has a lot of role to play. And if, for example, you had the ICP information as well, then I would be confident in saying, yes, we could. So we have this dream, to be honest. Imagine a software where you input all of the details that you have about a particular sapphire, from the trace chemistry data to the different spectroscopic data that a gemological lab can easily gather. And then just feed all of this information in, and then you would get all of the possible treatments that this material has gone through. And that would be the dream.
So you'd have to create an algorithm.
And also, more importantly, a database. A database that would be able to include all of these different defects.
Yeah.
And that database is absolutely crucial. And
It's actually quite possible. It just requires the
will.
Yeah, exactly.
It requires the will, because these calculations take time, they take resources, and but it's possible.
Hey, you have a supercomputer. Come on. Not every gemology laboratory in the world has a supercomputer to play with. So I'd like, Jolian, if you could unmute everybody, or if anybody particularly wants to ask a question. This has been a very technical presentation. So we're down to 33 people now, and would like to find anyone who's here to ask a question for clarification or education. Please do it now.
Or you can post your question in the chat, of course, if you prefer.
I hope it wasn't too technical, but we tried to.
I think having an understanding of processes are important, but from a gemological standpoint, ultimately, I think the outcome that would be beneficial in terms of real world would be to have tools and telltales that can help people analyze and determine whether a stone is naturally colored or treated. And I think what you're saying
Ray,
now
to be
is,
honest, yeah, I think we have well past that point. it's not that easy to be able to find the telltale signs through a simple examination under a microscope.
Yeah.
That is the reason why labs like the GIA are investing so much on these advanced equipment. We need a combination of all those equipment to be able to actually tell if a particular treatment has happened or not. So
Even then, there
yeah,
may be doubts.
even then
about
there are
the
doubts.
process.
So I truly discourage trying to find the answer to that question through simple gemological processes that a jeweler is usually familiar with.
So really, this is going to be limited to the major stones then. No one's going to want to be bothered doing this on a 3 or 4 carat or something like that. It's going to be something that's significant to warrant the cost of that kind of testing. So do we now then just assume that everything is treated?
I
pretty
think that's
well.
a good that's a good assumption. Yeah, stay on the safe side.
I mean, if
We're
I
getting-
make a comment, Ray, on this, as soon as you have any sort of clear and easy test that something is treated, then that gives the treatment industry a target for working around it. So you have your rules about what you identify now, or how you can identify something now, may be invalid in 5 years' time, as it's a game of cat and mouse, where clearly anyone treating stones is going to want to hide it.
You're absolutely right, Julian. I couldn't agree more. And in fact, you know, we have a little bit of an unorthodox view on this, and that is the following. In our opinion, we should outrun this game of cat and mouse. What do I mean by this? So if gemological labs start to play this in a little bit of a different way, if the gem labs not only play on the characterization and the identification side, but also start to play on the treatment development side, then, and they outrun the treatment industry in terms of their methods of treatment becoming so good that the treatment industry starts to follow them, then we are the winners. Until then, there is no hope.
Because right now we're one step behind the treatment
Community. And you know, it's very easy to change this game because the treatment community is not doing this using sophisticated scientific methods. They are just playing around, and just once in a while they find
trial and error,
Yeah.
actually. So their findings
They're
are
cooking
based
and
yeah,
looking, basically.
absolutely.
exactly. They're cooking and looking, and these processes, these heat treatments, do not require a cook and look approach. They can be designed much better than anyone does it currently in the industry. And you know, we are very supportive of standardization of heat treatments because consider the steel industry. About a century ago, a samurai sword was only the samurai knew how to, you know, make those fascinating swords made of stainless steel, and the methods were secrets. The heat treatments were phenomenally secretive. Today, we are in a very different position in the steel industry. For example, we have handbooks and handbooks of heat treatments of steel, which have been standardized. Why? Because the industry realized that if we want to do this professionally, we should change our ways. And I think the gemological industry, the gem and jewelry industry is on the verge of that transition. So once the gem labs start to do the kind of research that they're doing on diamond in sapphire, so for example, consider the GIA, they have their own CVD lab where they grow the diamonds. And a lot of research is very good research is coming out of their own CVD grown diamonds. So they have left this aside in terms of following this industry in a statistical manner and started to do the experiments themselves. Now they would have access to information which is not dependent on what we get from the market, but based on their own research. we need something similar on treatments, especially on treatments in colored gemstones. I think that is the future, and I hope the gem labs move towards that direction. It's not that difficult. It just requires some efforts.
So just a quick question here then. Spectrographic analysis that is obviously gotten to a new level than what it used to be. But in terms of the kind of laboratory equipment that a standard gemology lab has, are there any little tool tricks you can use to identify things using standardized equipment?
Of course. I mean, we can always. So this cat and mouse kind of a game is the following. We can always say that a treatment of this sort has been very likely, but we cannot create the conclusive identification. Is what we're trying to say. So yes, of course, there are, by using the combination of the current methods, spectroscopic methods, and especially through further research, this can become more and more and more trustworthy as things move on. And I think over the next few years, with the current pace that the gemological research has, I think things will become a lot more secure as well. So I don't think it's a gloomy future. It's a very bright future. And people are moving in this direction, especially, for example, in the case of low temperature heat treatments. Very good research is coming up on using Raman, micro Raman, on the zircon inclusions in sapphire.
I heard about that.
That's phenomenal. That's phenomenal. That's the way to go. And that requires the kind of efforts that we're talking about. If the labs start to do their treatments themselves, and then they do all sorts of equipments they can possibly use to find all of these changes that these treatments induce, that's a very valid way of doing it. Another valid way would be to calculate, like what we just mentioned. It's possible to calculate them as well. So it's an interesting fact.
I think we do have a question here. So you can actually reach our social media.
Why don't you just type down our?
Yeah.
Yeah, so we use Instagram a lot, and
You're also on LinkedIn
Scientist.
or Facebook as well. So feel free to follow us over there.
I'm just typing in the feed.
Have you filtered through chat? Do you have any other questions there?
So these are our Instagram accounts. And on Facebook, I believe if you just search
Type in our name, you can find us.
But we use Instagram more than Facebook. So. Yeah.
So you guys, if I can have a little chat with you guys on Messenger or one of those sometime next little while, we can prepare for the next one.
Sure, absolutely. And
Thank
also, we would love to hear your feedbacks regarding if it was too technical, we can reduce that. If it was,
Sure.
we can
recommend.
optimize accordingly.
We'll think about those things offline. But thank you first of all very much for the work you put into this.
Our pleasure.
I can sense, this is a passion for you guys, and the science of your background came through very clearly, and your ability to speak about it was actually quite good. So thank you, and we're looking forward to the next 2 months, and we're going to move ourselves along that spectrum of learning thanks to you guys.
Thank you so much.
It has been a pleasure. Thank you very much for giving us this opportunity to share this little bit of information that we have.
Okay, well, thanks to the three profs here. And thank
Thank
you
you.
to those in the audience that persevered. And we'll look forward to seeing you all next month. And those who are interested in going to Madagascar and see it in the flesh, in the mines, in person, get a hold of Ida Chow through the connections that she put up on chat. So I think there's an exciting adventure in the future for some of you who do go on that trip. And also, I'm hoping we're going to learn a lot more over the next 2 months from you guys. So thank you.
Thank you so
Thank you.
much. We truly appreciate it.
And thank you, Jolion, for overseeing this. And hopefully if you guys recorded this as well, did you?
No, we didn't.
No.
Oh, you did? Okay, well,
But it's okay, it is recorded. It's fine.
hopefully Jolion will throw it out on the web pretty quick.
Mhm.
Okay, well, look, thanks, everybody. Thanks, Jolion.
Thank you.
Thank you. Have a wonderful day. Thank
Bye-bye.
you.
Thank you.
Bye, y'all.
Bye.